Okay, let's get started. Welcome to 240, and Happy New Year to you guys as well. See a lot of familiar faces. Glad you guys made it back. Also some new faces. Just out of curiosity, how many of you guys are undergraduate students in this class? Okay, so that's great. We have a healthy group. And how many of you guys took 142 with me last semester? Okay, maybe about half the class. Okay, that's good. All right, well, as you know, the topic of this class is CMOS, analog integrated circuits. The focus will be CMOS technology, but every once in a while we may talk about bipolar technology as well. Today's lecture, this is actually lecture 2. Today's lecture is going to start out with kind of an introduction to the course. It'll be light and easy, give you a little break. I know a lot of you guys are back from vacation and maybe miles away from here mentally still. I know that I am, actually. So we'll have a nice soft introduction today, and then we'll start talking about process technology for the second half of this lecture. Okay, so some administrative things about this course. First of all, I have an aversion for paper, so almost everything will be online. You won't have any handouts. So it's your responsibility to go check the website and download the homeworks and the lectures and all that stuff, or hopefully just view them on your computer and save some paper, or save some trees actually. If you this is the direct link to the website here. It's my personal website. This first one is my personal website. There's also a link to the class website from there in case you're having trouble finding it. There is no textbook for the course. It's going to be based on class notes. There are a lot of excellent textbooks out there, and I've listed them under the references on the website, and I also put them on reserve at the library. I encourage you guys to look through these different books. They all overlap partially with the material that we're learning in this class, so it's a good idea to look at those books. And office hours. So office hours are going to be also the same day as the class, Tuesday, Thursday from 1 to 2. If this time is not convenient for you, you can just make an appointment with me. Okay? Questions or comments? Okay, for those of you coming in late, there's plenty of room, so first row is all empty. Don't worry, I don't spit. Okay, questions about office hours? Okay, good. So how about grading? Well, 20% of your grade in this class is going to be your homework, and 5% of that is going to be class participation. Now the reason that we put in this 5% is, this is first lecture that everybody's in here. By lecture 5 or 6, we might be talking to an empty classroom. So I want to meet you guys. I want to see your faces. I want to hear your questions, and I want to get to know you in office hours too. So if by the end of the course, if I look through those pictures and I don't recognize you and I don't really remember, ever talking to you, you're going to get docked 5%. So this is just to encourage you to be more involved in the class. Otherwise, the homework is very important. You're really not going to learn the material of this course unless you do the homework. And the homeworks, sometimes they can be very time-consuming. Other times they're really easy, no problem, just there to illustrate some concepts. So I encourage you to get started so you don't get trapped at the last minute, especially with the tools. Really early on in the course, get a handle on the tools that you're going to use in this class. You're welcome to use any SPICE-like simulator, Spectre RF, HSPICE, Eldo, whatever you like, but just make sure it works. Make sure it supports BSIM version 3.3 models. That's what we're going to have in this class. Otherwise, it's up to you what you want to use. Let's see. I guess for now that's all I'll say about the homework. Another 30% of your grade will come from a project. Now this is going to be a group project. I'd like to see maybe at most 2 people. If you like to work alone, that's fine, but it's also a good opportunity to work with somebody else and get a feeling for what it's like to work in a team. 30% of your grade will be on this project, so you can see that half of the grade is something where it's completely under your control, right? You have all the time in the world. Hopefully you have all the time in the world, and you can spend a lot of time with the homework and project and get half of your grade. The other half of the grade, actually, do these add up to 50? Okay. The other half of your grade, or almost half of your grade, well, actually, let's say with a 5% participation, then it does add up to, no, it's okay. Anyhow, we'll work it out later. As you can see, I'm not very good with math. So the midterm and final will be roughly the other half of your grade. I've tentatively scheduled the midterm for March 14th, and the final, of course, is set by university scheduling. Just to give you an early heads up, ISSCC is every year happens in San Francisco. This year it's February 5th to 8th. February 5th is actually a Sunday. Sometimes they have the short courses and things like that. So it's either Sunday or Monday when it starts. Oh no, Sunday there's a night session. But that week we're going to skip the Tuesday lecture. And I highly encourage you guys to go attend the conference. If you're serious about doing analog circuit design or circuit design in general, you really should go to ISSCC every year and take advantage of that. They have a discounted rate for students, so it's very reasonable. It's gotten a little more expensive, but it's still reasonable, and probably you won't even be paying. Your research advisor will be paying. And of course, you know, I've already looked up spring break, and I'm looking forward to spring break. So, okay. So, any questions about the administrative part of the course? Yes.
Is the project going to be throughout the whole semester?
No, the project will be the second half of the semester, and I'll still working on the project and making sure that our models are good, and hopefully once we go through a few homework assignments and get rid of all the bugs in the models, then we can actually assign a good project to you guys. Okay. Any other questions or comments? All right, so basically you might be wondering, some of you, why even study analog circuits? It seems like the world is becoming more and more digital, and why is it that the world is really becoming increasingly digital? Well, one of the reasons is that, of course, it's the famous Moore's law that if you look at the cost of building a digital circuit for the same amount of functionality, it's decreasing rapidly, so about 30% per year. And it's really staggering when you add that up over the years. When you compound that over the years, it's exponential growth. It's like your retirement. Well, that's 30 times in 10 years. So if most of you guys probably 10 years ago did have a computer. Just think about what CPU clock speed was, how much memory you had, how much hard disk space you had. It's really, really amazing how much more powerful computers have become. I remember when I was a grad student, I'd go to talks and people would talk about decoding MPEG files. And at that time, you could not decode them in real time. If you took like the best workstation and decoded it, it would take like 3 times longer than the actual time. And so people were trying to find more efficient ways to decode an MPEG. Well, nowadays, if you're playing an MP3 file on your desktop or laptop, and you look up to see how much of the CPU it's taking, it's negligible, right? It's taking less than 1%. I mean, you can do it for free. So things have changed a lot. Just to give you a reference point, it's always good to talk about your first computer, because that tells people how old you are. My first computer had 4K of memory. That's right, 4,000 bytes of memory. Of course, it didn't have a hard disk or anything like that. So today, you go buy a computer, you can't get less than half a gig of memory, right? Even if you don't want it. So how does that compare with analog circuits? If you now go look through ISSCC past 10 years and you look at analog circuits, you realize that the same benefits don't apply to analog circuits. In fact, analog designers in many ways have been working really hard to deal with this constantly changing technology. For the digital guys, it's gotten better and better. For the analog guys, it's gotten harder and harder to build high precision amplifiers with lots of gain, with good matching, with good yield. That's because, as we'll see in this course, the cost per function is actually going to be constant for analog circuits. And some of the things that that you really are difficult to deal with are reduced supply voltages. So as you guys all know, as we scale technology, we also have to scale the voltages to keep the fields roughly constant to basically mitigate short channel effects, high field effects. And that means the voltage has dropped dramatically from tens of volts when I started in this industry, now down to a volt. And it's gotten very, very challenging to design circuits in that. The other thing that we see that's happening is that DSP technology, digital signal processing, is also benefiting directly from the improvements in digital technology. And that means that more and more functionality is really going to digital. So, again, 10 years ago, a filter for a phone would have been an analog filter. Today, it's probably a digital filter, right? It's completely implemented in digital technology. So the question is, why is it that we're still studying analog circuits, So one reason that we are studying analog circuits is that no matter how good digital technology gets, we still live in an analog world, right? Or if you really want to get technical about it, and say there's quantum mechanics and that even our sensors are really digitized. Okay, we could get into a philosophical discussion. But for all practical purposes, the real world is analog, right? And so there's always going to be an interface from analog to digital. So analog designers will never go out of business because they still, at the end of the day, they have to convert information to digital. And that's not a trivial task. If you want to take an analog signal and digitize it, it's actually one of the hardest problems in analog circuit design. And if you go to ISSCC and look at the analog sessions, you find that that's actually a big portion of the analog papers today. Most of the analog designers in the world are actually working on analog to digital converters, and the opposite, digital to analog converters. Where else do we see analog circuits? Well, when it's in the critical path. So I'll ask you guys to give me some examples. Besides ADCs and DACs, can you guys think of some areas where analog circuits are still important? Okay, guys are quiet today. Remember, 5% of your grade comes from participation. So this is an easy way to get involved. Okay? So why are you guys in this class, right? I'll turn around and ask you, why are you taking this class? All right. So I'll ask Simone, since he's an experienced analog designer, why are you in this class? Or why do you study analog circuits? Make sure to use the mic.
Unclear to me.
Okay. Is it clear to anyone else why you're in this class? Okay. While you guys are thinking, I'll make a couple of announcements. I just remembered with the microphone. As you know, you probably know, this is going to be webcast, so you can watch these lectures at home. This year it's also going to be podcast, so you can download it onto your iPods or whatever you like. I don't think that includes video, it's just audio podcasting. So it's critical that when you guys participate for your 5% of the grade that you also use those mics, because it's really annoying if you're watching a lecture and there's a question and it's just that you don't hear it on the recording. Okay? So, back to the question at hand. Why are you guys in this course? Okay.
So I work with the CTC converters, and many of them are still analog, and it looks like they will be for some time.
Okay, that's actually a good area that I didn't put on this list here. Yeah, DC-DC converters. So even if you're building digital circuits, they need to be powered up, right, from a battery. And you don't simply connect the battery to the IC. There's actually lots of circuits that go between the battery and the IC, not only to change the voltage, but also to be able to supply the right amount of current, to minimize the ripple on the supply, to be able to handle a varying load. So designing DC-DC converters is actually a big area of analog circuits. And amazingly, the technology to build DC-DC converters is very old. You can go look at a catalog from 10 years ago and you see that, yeah, DC-DC converters have been around for a long time, and yet there are companies out there that are making a lot of money from DC-DC converters. That's because any product that you have, your PDA, your cell phone, your laptop, they all need DC-DC converters. So that's actually a big area for analog. Okay, anything else that you guys can think of? Okay, you guys are shy today. So I've listed a few applications here. MEMS, basically, more generally, any kind of circuit that has to convert from other kinds of analog signals, right? Not necessarily voltages and currents, but perhaps mechanical vibrations, temperature, pressure. So any time you have an interface between a sensor and a circuit, you're going to need some analog circuits to do some signal processing. You can't, for instance, if you've got, let's say, a mechanical resonator that's picking up vibrations in the air, you can't simply digitize that signal. You have to do some kind of analog signal processing. We'll talk a little bit about how analog fits into RF transceivers. A transceiver is a receiver and a transmitter. That's because transceivers are very important. You all know that wireless communication is a very important field. Another area is wireline communication, high-speed wireline communication. So the interface, let's say for your USB 2 cable, or your FireWire cable, or some other kind of link, that's essentially a digital system, right? Why would we care about it from an analog perspective? Well, if you go and look in there, the speeds are high enough and the interface is complicated enough that you really have to understand the terminations, the analog signal properties. You can't just treat it as a digital system. Okay, so it's always good to step back and review what really is the differentiation between a digital system and an analog system. And I wrote down a few ideas. If you guys have some, let me know. We'll add them to this list. Most obvious is, of course, the abstraction. Digital circuits have a very nice abstraction, basically zeros and ones and Boolean logic. Nowadays, most people don't even deal with digital at that level, right? You deal with it basically at the architecture level, where you talk about registers. For instance, you could specify a system using register transfer logic. What's the abstraction in analog circuits, right? It's a kind of an interesting question. Progress is made by making abstractions, right? If you tried to go out and design a circuit and you didn't make any kind of abstractions, you'd be in trouble. You'd have to consider, right, everything we know. You'd have to consider quantum mechanics. You'd have to consider thermodynamics. You'd have to consider, Maxwell's equations, Schrodinger's equations. It'd be ridiculous, right? You couldn't do anything. You'd be stuck. So you have to make some kind of abstraction. You have to say, well, I'm going to treat everything below this line with this black box, right? And in analog circuits, the abstraction is actually your device models, right? Your transistors are your building blocks, and the way you understand your transistors is that these transistors are described by some model. Now, in your first circuits course that you took, probably the model you used was something like a square law model for a transistor. We're actually going to use that model partially in this class as well. It gives us a lot of insight. It's very simple. But if you're going to do any kind of serious design, you have to use something more sophisticated. Today, that's some kind of transistor model. Often it's a BSIM model. BSIM is as most of you know, is basically a standardized model that has hundreds of parameters that describe the transistor behavior. And these parameters are given to you by the fab, the person who fabricates your circuitry, characterizes these transistors and describes them instead of giving you raw data, they give you BSIM models or BSIM model parameters. And your simulator knows how to interpret those parameters and can simulate circuits for you. Now, BSIM actually has a long history. It started here in Berkeley. In fact, the B in BSIM does stand for Berkeley. But, you know, if you try to use that as an abstraction and you go look at basically the BSIM manual, it's a thick manual. You can read through it. There's hundreds of equations in it. And then you might be unsatisfied and you want to actually look at the source code. It's available on the internet. You can download it. It turns out it's a few thousand lines long, right? So our abstraction for a transistor is actually a few hundred equations or a few thousand lines of code, right? That's pretty tough. And I think in some ways that is the first reason why analog designers are respected and they get paid so well, is because they can deal with complexity. Of course, we're not going to go and look at all those equations in detail. We're going to learn how to abstract away a lot of that detail. That's because what we're really interested in is oftentimes in this course the small signal behavior of the transistor. We're going to be dealing with linear circuits, and you don't need thousands of equations to understand the small signal behavior of a transistor. Okay? Now, in this class, it's really the transistor that reigns supreme. If you take other courses that are analog courses like 247, you're going to be building analog systems, and again there's going to be a level of abstraction. You're going to basically think of analog circuits in terms of OTAs and op-amps, and you're not going to spend too much time thinking about what's inside those op-amps. You're going to just assume that you can design an op-amp that meets a given spec, right? So what you're going to get from this course is, if someone gives you some specifications for an op-amp, this much gain, this much settling time, right? This much accuracy, this much noise, this much offset. You can translate that into an actual design. So that's the skill that you're going to learn in this class. Okay. A couple other things to note. Today, if you do digital design, it's highly automated, especially if you're doing non-critical speeds or, let's say, moderate speeds. That means you write some code, you push a button, and out comes a chip. You know, so really a good digital designer doing that level of design is really someone who understands all the tools and the interactions between the tools and knows how to get the tools to give you the right answer. Layout, therefore, is pretty much automated. You know, you don't go in and touch transistors in that kind of situation. You just push a button and the layout is generated for you. It's very nice. It's very fast. Analog, though, by and large, is still handcrafted layout, and analog designers take pride in the way they do their layouts, because the layout has a big impact on how the circuit actually performs. Okay. There are companies where they have layout engineers who are experienced layout people who kind of handle the layout more from an artistic perspective rather than a technical perspective. But they again work very closely with the designers to make sure that the layout is done right. Now, there are a few companies that are trying to solve this problem for analog, because obviously doing hand layout is time consuming, and they're making a lot of progress, but still today, by and large, the analog layout is done by hand. Why is that? Why do we do analog layout by hand? Seems like a no-brainer. I can give you guys a project to go home and write an automated layout routine, right? Given a bunch of transistor sizes, you can come up with an automated algorithm, right, that generates a layout for you. Okay, why is it that we spend the time to actually do this by hand? Okay. Yes.
The actual positioning and the distances can be important, and matching between two sides can be important, and sometimes it's hard to get that intelligence into an automated system to know what is important to be placed close and what isn't important to be placed close and things like that.
Yeah, the key word is matching. So matching is very important in analog circuits, and we'll talk about that a little bit this lecture and probably next lecture. Also, the parasitics are huge, very important, right? So when you do analog layout, if you lay things out in a stupid way and you put one transistor really far away from the transistor that's driving it, you're going to end up with all this parasitic, and it's going to really impact the performance of your circuit. And those parasitics, you can estimate them now in an automated way, so that you can extract capacitance and resistance, maybe even inductance for really high-speed applications. But the extractions are not very accurate. Their accuracy is on the order of 20–30%, and they're also very time-consuming. So to do an extraction for thousands of different possible layouts, very quickly the different number of combinations explodes and makes the layout very, very time-consuming to do in an automated fashion. Whereas for a person doing layout, if you have 100 transistors a layout and only 10 of them are really important, you're going to spend all your time with those 10 transistors, and a machine doesn't really know a priori which transistors are actually important. Okay. Now, many of you guys took 142 with me last semester, and you got some experience with RF design. So another good question is, what's really the difference between analog and RF? Okay, and basically, kind of joking, you could just say RF is analog, but you've got inductors, right? That's the big difference. But there's a lot more to it than that. In RF circuits, usually we're dealing with narrowband signals. So somebody modulates a signal, and the modulation is actually much less than the carrier frequency. So you might be transmitting a gigahertz and you have 100 kilohertz of modulation or megahertz of modulation. So for all practical purposes, your signals are narrowband. And that's actually really nice because you can use tuned circuit techniques. You can put inductors, resonate out capacitances. That lets you push your transistors to higher frequencies than you would be able to otherwise. And so almost all the circuit techniques are in some way sinusoidal. So frequency response is very important when you're dealing with RF circuits. Another big difference is in RF circuits, the impedance levels tend to be very low, right? Everybody knows universal 50 ohms, right? Or 75 ohms, if you're dealing with cable. Why is it that we use low impedances in RF circuits? Okay. Anybody? Well, part of the answer is written on this slide. Come on, guys. You guys have to participate. It's no fun if I do all the talking. Okay, I'll call on people. Debo, why do we use low impedances?
Better power handling capacity.
Okay, that's a good point. If you look at transmission lines, for instance, and you look at how much insertion loss you get at a transmission line, it turns out it's better to use impedances around roughly 50 ohms. The other answer, which I've written on the slide, is for wideband operation. The lower the impedances that you use, the smaller your RC time constants are going to be, right? And since RF signals often interface with the external world where you have lots of capacitance, it's nice to use low impedances for that reason. Now, analog circuits, on the other hand, like high impedances for voltages or very low impedances for currents. And that's because a lot of the signal processing that we're going to be concerned with is on chip, and we want to get, oftentimes we're just trying to build circuits to get as much gain as possible, right? And if you're talking about voltage gain and you have a transconductor, obviously you want to use the highest output impedance possible. Which brings about another distinction between RF and analog. In RF circuits, a lot of times we're concerned about power. We want power gain. We want our LNA to have power gain and low noise. We want our power amplifier to be able to deliver a certain amount of power. In analog circuits, though, we're processing the signals, and a lot of times the way we think about it is in terms of voltages and currents. Okay, so the signal processing is done with voltages and currents. Another huge distinction between analog and RF is the idea that if we're going to digitize our signal anyway, right? In fact, I'm going to do a lot of analog signal processing, then I'm going to convert it to a digital bit stream, right? Well, that gives me the flexibility to discretize the analog signal. In other words, I can sample my analog signal, and I only care about those samples. By the sampling theorem, we all know that we can reconstruct a band-limited signal, right? And so I can process my signals in a discrete time fashion. That's a big distinction between analog and RF, and we'll take advantage of that in this course. Okay. Questions or comments? Okay, so here's a more concrete example of a wireless system. What I want to point out here is that even in a wireless system, in a so-called RF system, there's still a lot of analog signal processing. Okay, and some of that is RF, but a lot of that still today is pure analog, what we're going to talk about in this course. So, without going, boring you guys with the details here, in an RF system, the main task is frequency translation. You want to translate, I think I have a slide here, yeah. So if we look at more closely at a block diagram of an RF system, then, what we call the RF stuff is kind of here, right? This is the RF stuff. Here we do some amplification with low noise, we do some frequency translation with these mixers, we do frequency synthesis with this VCO. These are nonlinear building blocks. But then once we bring the signal frequency down to this intermediate frequency, from here forward the processing is mostly what we call traditional analog signal processing. So that usually is filtering, some further amplification, probably a variable gain amplification or an AGC circuit, automatic gain control circuit, and then some more filtering, and then basically digitization at the very end. Okay. Here is a layout of an RF transceiver, and again, if you look closely at this, a good way to figure out what's RF, what's analog, is anytime you see these little spiral inductors, that's probably RF, right? They're using inductors. So here you can see the VCO and the PLL. PLL, though, is kind of a mixed signal circuit, and we'll talk about that a little bit. But here you can see that these baseband circuits, these amplifiers, this amplifier chain, these filters, these are all pure analog circuits, and they take up about half of the die area. So you can see that if you're designing, in this particular case, a wireless LAN transceiver, you still need a lot of analog designers on the team. You can't just do it all purely in RF and digital. Another trend that you guys may have observed is that traditional RF is also starting to look a lot more analog. And so in this example, I've shown you a kind of a classic RF amplifier that you would use as an LNA. It uses inductive degeneration to synthesize a real input impedance and have low noise. If you look, it uses shunt peaking, has a filter at the input. You can see that if you look at these inductors, we've got probably 5 or 6 inductors in this simple amplifier. Why is that a bad thing? Why not use inductors?
Take up space?
Yeah, they take up a lot of space. If you look at this layout again, you can see these little empty spaces here with, where this inductor is. That's a lot of area. And you're also pretty much prevented from putting anything inside or around these inductors. You like to keep them clear. So the typical area for these inductors at these frequencies might be, let's say, 150 micron squared by 150 micron. So that's quite a bit of area. If you go to an analog solution, so here I'm using shunt feedback to basically synthesize a low input impedance. I just need to use resistors, okay? And resistors are much smaller than inductors. So this, if you compare the layout of this to this, it might be 3, 4, 5 times smaller. What are some of the other benefits of using analog circuits as opposed to this circuit on the left? So here's a question for those of you guys in 142. What are some advantages for the analog solution? Maybe somebody who hasn't answered yet. Yes?
The analog is broadband?
That's right. The analog is broadband. That's a good point. This circuit here, because it uses so many inductors, tuned circuits, You have multiple LC tanks. You have to make sure they're all tuned to the same center frequency. Any kind of process variations is going to basically make it difficult for you to do that. Any kind of routing parasitics as you go to higher frequencies is going to impact the amount of inductance you have. The analog circuit, though, is pretty broadband, and as long as the bandwidth is larger than what you need, you're set. Okay. How about some other advantages for the analog circuit? Okay. Michael, Mark.
Yeah, you can also have cross-coupling between the different inductors.
That's also a very good point. Because these inductors are physically large, they are easily inject signals into the substrate and also capture signals from the substrate. And the same for stray magnetic fields. So if you're building a complicated IC and it has, 20 of these inductors, and one of the inductors is in the power amplifier, another one's in the VCO, you better be worried about the coupling that's going to happen between that power amplifier and that VCO. Okay? If there's time in this course, towards the end, we're actually going to spend maybe a lecture or two on coupling issues in analog circuits. So it's a topic to keep in mind. Okay? Any other advantages? For those of you who took 140 last semester, what's the advantage of stability? Okay? Well, that's kind of an issue, right? It's something we have to worry about. What's the advantage of this analog? Compare left and right. What do you have a lot more on the right-hand circuit than you do on the left-hand circuit? Feedback. That's right. Analog circuits use feedback, right? And feedback is really good because it makes the circuit performance essentially a function of your feedback network. So as the process varies, as long as the ratios of the resistors track fairly well, this amplifier's performance is going to track fairly well. The circuit on the left essentially is open loop. Now, it does use some local feedback, right? It has this degeneration inductance. So technically it also uses feedback. But if you vary the process to the temperature, the circuit on the left is going to vary a lot more than the circuit on the right. What's the price that we pay for using feedback in this particular example?
Your FT has to be a lot higher than whatever your bandwidth is.
That's right. You could, because you're using tuned circuit techniques, you can pretty much operate at really, really high frequencies, even approaching the FT of the device. You can build this amplifier and it'll work at the FT. We'll talk about FT a lot more next lecture, but it will work at the FT of the device. The right-hand side circuit, though, has to operate at some fraction of the FT. Why is that? Why do we have to operate a fraction of the FT? Maybe somebody else. Yes?
You tend to have a constant gain bandwidth product.
Well, let's say I didn't need a constant gain bandwidth product. We'll still favor operating at a fraction of the FT. Anybody else want to take a stab at it? And use the mics.
Noise?
Noise. Let's talk about noise later. Okay. Your break wasn't that long, right, you guys? You're either shy or you had a really good break. Okay. Anybody else? Come on, you know the answer, right? You guys all took 140. Anybody? Why not just build this amplifier and make it work at FT? Right? Well, what would happen if you try to do that?
Stability?
Yeah, stability, right? It's so easy. There's going to be right when you build any kind of feedback network, there's non-dominant poles, right? And those non-dominant poles are going to determine the stability, the closed loop stability. Those non-dominant poles are all going to be on the less than FT, on the order of FT, let's say. So clearly you can't build a circuit that operates all the way out there because it's going to be unstable, okay? All right. Here's another example of an analog circuit. This one comes from Professor Boser and his students. And this is basically a MEMS accelerometer. Now, the way these things work, anybody in this class work with MEMS? Yeah, why don't you tell us how this circuit works?
I don't know this one.
In general, right? General concept.
Okay, the displacement of the proof mass is capacitively sensed, and then that signal, usually a current, is then translated into a voltage and then digitized.
That's right.
And it's
That's right.
used in a feedback loop. They use force feedback to suppress the motion so that you get better linearity. Basically, you don't expose yourself to the duffing linearity of the spring system.
Okay, let me draw a picture for what you just described. So the idea is that you're going to build a structure like this that has these fingers, and this is going to be a polysilicon structure. So in fact, this is really just a capacitor, right? And the capacitance is a function of basically the spacing between these fingers. So if you have, let's say, a displacement in this direction, the capacitance will change a little bit, right? Because it's mostly lateral capacitance here. But if you have a displacement in this direction, you can see that this is going to get close here, further here. The capacitance between this node and this node really is a function of the displacement, right? And so the idea is that I want to sense how this capacitance varies. I want to build a circuit that can sense the change in this capacitance. Now that's an analog circuit. It's not easy to do that directly with digital circuits. And in fact, we can improve the performance of the structure, as you mentioned, by using feedback. So instead of basically just letting the structure move around on its own, what you can do is you can use feedback and force the structure to always be in a given position, in a fixed position. And then you can use how much force do you need to impart on the structure to keep it into a fixed position. By knowing that force, then you know exactly how much the structure is accelerated in a given direction, right? And what's amazing, let's go back to the slide. What's amazing about this kind of circuit, you can see here it has, it can sense different axis displacement, x-axis, y-axis, z-axis, is the precision of these circuits. These circuits can actually detect motion on the order of angstroms. So movement on the order of angstroms can be detected by these accelerometers, right? It's amazing. How do you do that? Well, take this course and understand how you build analog circuits that have the required level of noise and linearity to process those kinds of tiny signals. In fact, it's below angstroms, right? What do you have a number for us? What's a typical resolution? Yeah, it's not important. Yeah.
Actually, it's on the order of 1/10 of an angstrom.
Wow. 1/10 of an angstrom. Pretty amazing, right? Typical atomic spacing, right, is on the order of angstroms. So it's, basically detecting something on the order of, the radius of an electron, the classical Bohr radius of an electron. Okay. How about some other reason? How many of you guys here consider yourself digital designers? Okay. Just one person? You don't have to be shy. We won't beat you up. It's okay to be a digital designer. Okay. Well, good digital designers definitely need to know some analog. And one of the reasons is that, classically, if you look at a digital designer, the model of the transistor they use is something called the Bush model of a transistor. In other words, they say a transistor is a switch. It's either on or it's off, right? If you look at a modern transistor, right, you need something a little more sophisticated. It's not going to do, because it's basically hard to turn off that transistor. It likes to leak. The gate is leaky because you use a thin oxide, and it's also the drain is leaky because, you know, you're basically going to have subthreshold conduction, and that's going to impact your design. So a modern digital designer who's actually designing at the transistor level really also needs to understand the properties of that transistor. And as we've mentioned, you know, these medium frequencies, digital designs are just push button, but cutting edge design or designing for a critical path really does require sizing transistors and going in and carefully examining propagation delays through networks, things that are very similar, analogous to what we do in analog circuits. If you're designing I already mentioned this, I'll say it again, if you're designing digital circuits that have to drive anything off chip and your clock frequency is on the order of a gigahertz, you're going to basically have to know your transmission line theory. You're going to have to think about step response, ringing, all the good things that we talk about in this course and other courses are going to come into effect in those digital circuits. Something which is much newer, a new concern for digital designers is matching. Traditionally, digital design, matching is no problem, but as you've made these transistors smaller and smaller, the actual doping in the transistors has gotten to be to the point where a few dopant atom fluctuation results in a large fluctuation in the VT of a transistor, right? If you're using a very, very small area and you calculate, let's say in a small volume, in fact, let's see if we can just back of the envelope do a calculation here. Let's say I have a tiny transistor, has a dimension of half a micron by, let's say, 0.1 micron, and let's say I want to dope this at 10 to the 18, okay? And let's say my dopants are going to go in also, I'm going to round off here, let's use 1 micron, and here let's use 1 micron, okay? So what's the volume of this guy? The volume is 1 micron times 1 micron times 0.1 micron. So that's 0.1 times 10 to the minus 6 times 3, or 10 to the minus 18, right? So if I invert this, I get, so this is 1 times 10 to the minus 19, so 1 over the volume is 10 to the 19. So if I to put 1 dopant into this volume, the density would be 10 to the 19. But this is per meters, not per centimeter, right? Okay? So the conversion factor is 10 to the minus 2 cubed, or 10 to the minus 6, right? So per centimeter, this is still pretty healthy doping, right? As you shrink this volume down more and more, very quickly, you know, this dimension shrinks, and you get into the situation where instead of having 1 million dopant atoms, you end up having just hundreds of dopant atoms, okay? And then when you basically fluctuate just a few atoms, you find the threshold voltage fluctuates considerably. So if you're dealing with new technologies, let's say below 45 nanometers, then fluctuation of dopant atoms is a huge effect, okay? So that's one issue. So your VT of your transistor is going to be a strong function of your doping. What's going to be another issue for your transistors if you're building really, really tiny transistors? Yes.
Source channel effect.
I'm sorry?
Source channel effect.
I'm sorry, can you say that?
Source channel effect.
Source channel effect?
Yeah.
What do you mean? Short channel. Okay, yeah, of course, we got to deal with short channel effects. That's I've had to deal with that for 10 years. But another thing that comes out is basically as you make these dimensions smaller and smaller, and I build a transistor, right? I may draw it like this, but what I actually get is something like this, right? So the roughness, the line edge roughness. So as you make things smaller and smaller and you approach, let's say, nanoscale, then these kinds of natural variations that occur in real structures are really going to start to be important. Over here, for a long channel transistor, you don't even see it. It's so small. Okay? So digital technology today, for the first time, is getting to the point where you have to worry about these kinds of variations. If you're going to design, you know, a megabit of memory, and you want a good yield out of that memory, you better worry about matching issues, okay? Process variation. Okay, what's another important, so you know, I asked you guys how many of you are digital designers. Only one person kind of raised their hand. So let me ask another question. How many of you guys feel comfortable with doing digital and analog design? Okay, I better see more hands up. How many people feel comfortable doing digital design? How many people have taken 141? Okay, you better feel comfortable doing digital design if you've taken 141. The reason that it's increasingly important to be adept at digital design, even as an analog designer, is you better take advantage of these so-called free transistors, right? You've got this 90 nanometer process, you put down an inductor, and let's say the area is 200 microns by 200 microns. You better have a good reason for using that inductor. Because you know what? You can build a microprocessor in the same area. So, a microprocessor or an inductor, right? LDI dt squared, you know, LDI dt or a microprocessor, right? So, if you can eliminate that inductor and do some more signal processing with that microprocessor, it's a win. It's a win because even though the area may be the same today, in a couple of technology nodes, the area is going to be much better for the digital. And the power is going to be much better for digital, right? So there's this concept of digitally assisted analog, and if you look at the websites for a lot of research groups around the world, it's kind of a catchphrase that people are using, but it's actually true, it's real. What's happening is people are realizing that to build good analog circuits sometimes involves a lot of digital circuits. In other words, the digital circuits can be there to aid you in achieving your analog functionality. There's some really obvious things. So for instance, if you're building this amplifier and you find the one on the left here, and you find that actually the resonant frequencies are a little bit off, what can you do with digital circuits to compensate for that? Well, you can just have some capacitors and you can switch them in, right? You can have an array of capacitors which are, let's say, binary weighted, and you can switch them in and out to get the right resonant frequency. Okay, that's a very simple example. You can do that with an oscillator to get the tuning frequency right. You can also use digital circuits to tune out offsets, right? So instead of spending all this area and power to build an amplifier that has a very small offset voltage, right? Let's say you're targeting a millivolt of offset voltage. Well, instead of using these huge transistors and all this current, as we'll see in this class, what you could also do is just measure the offset and subtract it from the input. And if you're in a system that's discrete time, that's actually very simple to do. Even in continuous time systems, you can do variations of that. So what we find is, at one level, we see that digital functionality is increasing in analog circuits. At a more fundamental level, we see a shift in the way people think about analog circuits. So by that, I'll give you an example. One of a PhD student who now is a professor at Stanford, Boris Muirman, did an ADC converter, pipeline ADC converter. And if you know anything about pipeline ADC converters, you know that there's very, very strict requirements on settling time of the pipeline stages, the gain you need in the pipeline stages. You need gain in the pipeline stages because you need accuracy, you need good linearity, because you're going to use feedback. Well, it's harder and harder to do that with the modern advanced CMOS processes. So instead of spending all his time trying to optimize the gain stages, Boris said, I'm going to use lousy analog. I'm going to just let the analog circuits make mistakes, and I'm going to use digital circuits to correct for those mistakes. So I'm going to somehow detect the gain errors, linearity errors, and somehow in digital correct for those errors. So that's a fundamental shift in the way you would design a circuit. And I think we're going to see a lot more of that as we go forward. Okay? Questions or comments? Okay, I think I said this already. There's also a lot of mixed signal design going on. So if you're designing things that, if you're designing a PLL, you can think of it as an analog circuit, you can think of it as a digital circuit, and you can think of it as an RF circuit. It's really all three. So really, all three skills come into play to realize a circuit like a PLL. It has frequency dividers, which are high-speed digital. It has filters, which are analog circuits, op-amps, which are analog circuits, and so on. Okay, so with that introduction, here is a syllabus for roughly some of the topics that we're going to cover. I should mention that this course is usually taught by Professor Bozer, and he's on sabbatical this semester, so I'm teaching in his place. So a lot of the notes that I'm using are based on his notes. We're making a few big changes in the course. One of the big changes is we're going to use a new process technology. I'll talk about that in a little bit. Depending on how far we go in the course, I may also emphasize or de-emphasize some of the kind of the applications that we look at in this course. So these topics are kind of the main topics that we'll cover. We're going to spend a fair amount of time on device models and simulation issues. We're going to spend quite a bit of time on kind of what we call support functions, things that may not be interesting, but actually are very important, things like biasing circuits, current mirrors, references, and so on and so forth. And then, by and large, we're going to spend most of our time looking at amplifiers. And the reason for that is, really, the amplifiers are like the gates of a logic circuit. They're very, very key blocks. We use them over and over again. We specify them in a lot more detail than you would specify a gate. You need to know a lot about an analog building block before you can use it. And you're going to need to know things like the noise of that block, its frequency response, its step response, its stability, and so on. The poles, the non-dominant poles, the accuracy of that block, how it varies with process, how it varies with temperature, what its offset voltage is. The focus of this course really is design. Okay, so I don't want you guys to lose sight of what's important, because a lot of times we're going to go in a fair amount of depth and talk about device models. That's not the focus of this course. The focus of this course is design. We're going to pick up the pieces that help us achieve good design. So let me contrast this course with some other courses that you've taken or that you may take. Probably you haven't taken 247. It's a prerequisite for that is this course. A comparison between 240 and 247. They're both analog courses. This course, as I've already said, is transistor level building blocks. There's very little abstraction in this course, right? As we mentioned, our abstraction is our SPICE models. And we use SPICE almost exclusively. 247, though, is kind of the higher level. It really uses the concepts from this course. So you may be building a filter, and in doing so you need a certain OTA, operational transconductance amplifier. Well, how much gain do you need, right? What's the noise? That's kind of 247. You come up with the specs, and then the role this course plays is basically we teach you how to design an amplifier that meets those specs. So in 247 there's a lot more abstraction. You use behavioral models, use block diagrams, use something like MATLAB or Verilog A to do your design. This course, it's mostly SPICE. Okay. Questions or comments about that? Who has taken 247 incidentally? Okay, a couple people have already. Okay. All right. Well, how about this course versus 242? I think we've already covered this distinction. Since a lot more people came in the class, I also want to get a sense again of how many of you have had 142. It looks like maybe a third of you have had it. Well, if you suffered through 142, the good news is that it will help you in this course. one area where it really will help, where there is some overlap, is noise. So we covered noise pretty extensively in 142. 240 noise is also going to be a big concern, so we're going to review the noise, and for those of you guys who've taken 142, you can basically go to sleep while we do the review. The focus will be a little bit different. We won't be using noise figure, for instance, in this class as much, if at all. But you know, the fundamentals are the same, so you have a little bit of edge there. Also, you know, really the background, the course you should be concerned with is 140. Anyone here not have 140? Okay, you guys are grad students. I don't need to worry about you guys. You've taken equivalent courses, I'm sure, before, right? If it's been a while since you've taken 140, you know, review your feedback theory. You know, go through the book. We're going to cover a lot of that again in this class, but obviously it'll be much faster. It'll be a quick review, and we'll use those concepts. Another note, just for those of you who haven't taken 142, there's a very good likelihood that I'll merge 142 and 242 into one course. And if you take 142 as a grad student, or even as an undergrad, if you do the class project, you'll be able to get graduate credit. You'll get 242 credit. If you don't, then you'll get just the 142 credit. Okay. Finally, just very quickly, how many people have taken 231? Wow, so we have quite a few people who have a good device background. That's great. Again, the emphasis is that in this class, we're going to pretty quickly abstract away the details, physics, right? We want to understand the physics, have a handle on them, but we're not going to obsess over them and talk about how to model them. We're going to assume someone else has done a good job of doing that. What we're going to do is basically, you know, in some ways it's funny. The only place that really concerns us is when we're doing the DC operating point of a transistor, right? That's where we need the full-blown IV-CV equations, mostly IV equations for DC operating point. And really, when we're doing design, we need small signal models. So what we'll find in this course is we're going to use the simulator to tell us the small signal parameters, right? We're not going to try to calculate those from a simple square law model, which is going to be grossly inaccurate. But once we do that, we can do hand analysis. So really, what I want to emphasize in this course is hand analysis. You know, good analysis of a circuit to understand the trade-offs in the design. And for the most part, the large signal relationship that you need is going to be abstracted away in the SPISM model that we're going to use. So if you've taken 231, it's going to help you to understand the modeling issues, and we'll review those very quickly in about one or two lectures. But the focus is on design, right? Okay, and I say that because it may be a little bit confusing and a little bit frustrating, because we're going to start out with the models, right? We have to, but that's really the only place we can start. And you might get a little bit bored. You might say, well, I know this stuff. Or you might say, you know, this is not why I'm taking this course. I took this course to do design. Well, unfortunately, we have to start there, and it's very important to start there, because another distinction I would make between a good analog designer and just an okay designer is an analog designer does understand the models very well. You know, I'm actually very involved with the modeling community, and when I visit companies to talk about modeling issues, typically I'll meet their device physics kind of people, their process people, and then in the audience I'll see a couple of really good analog designers, and they will be just as knowledgeable about the modeling issues as the process people. Of course, they have a different perspective, but they understand the physics. So I really encourage you guys to also spend some time and understand these important issues throughout this course. Just a quick reference. It's listed under the class website, but a really good book is written by Yanis Savidis from Columbia University. It's something like, let me see if I can come up with the title. MOS transistor physics, or... Very good. So somebody is familiar with this book. Operation and Modeling of the MOS Transistor. I put down the 1999 edition here. To be honest, the first edition is my favorite. It's the units especially are much more relevant in that book. It gives you a good perspective on the scale of analog circuits. But this is a very good book. It's written for you guys, for the analog people, right? You're the target audience, not a device physics person. So he never talks about the band diagram, right? And basically gives you a very, very in-depth, complete understanding of the operation of MOS transistors. And he builds it up very nicely, 2 terminals, 3 terminals, 4 terminals. So if you really work through this book, throughout this semester, and finish this book, or most of it, you'll come out with a really good understanding of the important issues in the device physics. I know for a fact that even people on the device physics side like this book and appreciate it. So it is a very good textbook. Highly recommend it. Okay. While we're here, I'll just talk a little bit about some of these other references. Most of you guys have a copy of Gray and Meyer, or the new edition with Lewis and Hurst, Analog Analysis and Design of Integrated Circuits. Highly recommended reference to have. I won't be using it specifically in this course, but basically, if you're serious about analog circuits and you're at Berkeley, you should probably work your way through this book, right? If you're going to take the prelim exam, for instance, you better know this book inside out. There's also some other really good references. Laker and Sanson is another good book that I highly recommend to you guys. Probably a new edition of this book is out, right? Anybody know? No? Okay. Another one is Johns and Martin. Probably, I would say that this book is really good for people who want to understand, one, the applications of what we're doing. So it's kind of a 247-ish book, but it's also a very nice, light introduction. So the style of the book, I think the target audience is, again, probably senior undergrads, first-year grads. So it's a very readable book. Okay. Questions or comments? And again, all these books should be on 2-hour reserve at the library. All right. Okay, so the question is, are you guys analog designers? Do you have what it takes? I was on the airplane last night putting this list together, so I probably missed a couple of things. But I tried to quickly capture some of the things that some of the skills that I've seen in good analog designers. First and foremost, there's a certain curiosity, that you want to know the details. You want to understand everything. You're a detail-oriented person. I think that the key to being a good analog designer is to be worried about things, but also to know when you can stop worrying, right? I'll give you a quick personal story. I met an analog designer who could just do layout at an incredible speeds, and I looked at his work and it was sloppy, right? I was just disappointed. It was really sloppy. And I went and I complained to him that, hey, your layouts are really sloppy. And he said, you know what? It doesn't matter. The stuff over there, it doesn't matter. The frequency's low enough, I don't have to care about it. I spent all my time on this layout. And that layout was a work of art. And that was for something that was critical. So in some ways, a good analog designer is a perfectionist only when it matters, right? You don't waste your time on little details, okay? At the same time, you don't assume that little details are unimportant, right? Hate to use these kinds of expressions, but the devil's in the details, right? Example of that in analog circuits is biasing, right? Now, my students, and I know a lot of you guys out there, when you design circuits, you think, oh, I'm in a university environment, biasing, I'm just going to take a pad out and I can bring in my external bias, right? So you're lazy. You don't spend time doing a good job on the biasing. And a lot of times you get burned because you pick up noise on that bias line, or it turns out to be really noisy, so you have to go out and buy a really low noise bias source. And in fact, if you had spent time on the biasing, you might have come up with some innovations in the biasing, right? So you don't just automatically say, oh, biasing is not important. You take it into account. You look at the process variations, the temperature variations, and you might realize that the proper biasing of the circuit is actually key for it to make it work, to give it good yield, to give it good production capability. So you have to be detail-oriented. You have to think about all these unpleasant things. Unfortunately, a lot of these unpleasant things aren't really in the model, right? So substrate coupling is not in your model, right? You can try to do substrate coupling analysis with tools that try to do it for you, but it's very painful and very slow. Package coupling, most of you don't simulate your circuit in the real package that it's actually going to end up in, or actually in the real environment in which it's going to reside, right? Do you know what chips are going to be around it? Do you know what coupling is going to come into it? Well, you should. You should think about these things, because these kinds of issues could end up being a killer. They might make your product unusable. And if you design a circuit and it works in your lab and your customer puts it in his circuit or her circuit and it doesn't work, boy, you're in trouble. You're going to have to spend all your time understanding why it didn't work in a different environment. Other things that aren't really in your model: thermal coupling, self-heating in the transistor, leakage mechanisms, extra leakage mechanisms, proper conservation of charge. As we'll see in this course, it's really difficult to trust the model's capability to accurately tell you where the charge is going in certain circuits, using capacitive feedback. So you're going to have to figure out if the circuit does the right thing. The model is not going to tell you if it's doing the right thing. And I've already mentioned that you should also, really, it's good analog circuit designers don't just understand analog design, they also understand process technology, they understand device modeling. And again, I should have put this on the list too. Good analog designers are like glue. They also understand the communication side, or the system side. So a system person is telling you need to meet these specs. If that system person is you have to know where those specs came from, because they might be impossible to meet for the first to start with, but also they may be overly conservative, or they might not have enough margin. So you have to really understand what's above you and what's below you. And what's above you is the system. What's below you is the device and the process. So you have to have a holistic knowledge of the IC industry to really create good integrated circuits for analog applications. Okay? Questions or comments? What did I forget on this list? I'm sure I left out a few good things, but okay, so let me just quickly have a few minutes. We can get started on lecture 2. Before I do that, let me just make sure that there are no kind of general questions about the course. As I mentioned, it's your responsibility to visit the website. If there are any important announcements, I'll try to put them up here at the top of the site. Check the homeworks link. Nothing is there now. Actually, why is there problem set 1? It's nothing. It's actually a fake link. I haven't made up problem set 1. I'll have the lectures for you guys, PDF files available. Also, I'm going to put today, if I don't forget, I'll put up the device models that we're going to use in this class. And I want you guys to really start with the models early. Simulate them, play around with them, get to know them very well. They're going to be your friends this semester. Okay? All right. So lecture 2, we're going to spend a lot of time talking about CMOS technology, and in particular we're going to talk about passive devices, resistors and mainly resistors and capacitors. Okay. Important question again. Why do this all over again? Right? Most of you guys know this stuff. Well, the key issue is perspective. We're going to look at this with a different perspective. We're going to try to come up with the metrics that are important in analog circuit design. So if you look at a transistor, if I give you a transistor, right, either data sheets or a model, what should you be concerned about, right? And a lot of it is going to sound very familiar to you. Some of it will be new for some of you, but we're going to care about things like current efficiency. In other words, how much gain can we get out of a transistor for a given current? We're going to look at speed. How fast can we operate these transistors? How much gain can we get out of these transistors? And how noisy are these transistors? So these are going to be the metrics that we're going to focus on. We're also going to spend about a lecture and maybe a little more on kind of the non-ideal effects in these short channel devices. So we're going to very quickly discuss why the square law model is not valid. It's a good point to start, because if we know what's wrong with it, we can focus on how to fix it. We're going to talk about what kinds of models we use for circuit simulations. So we're going to review aspects of BSIM 3.3. Again, we're not going to go into details on how the model works. We're just going to review the aspects of it. And again, we're going to focus on a model that we can use for design. So a methodology for using models that allow us to do design. Okay. Let me say a few words about our process that we're using in this class. Up to now, this class has been using a 0.35 micron process, and it seemed like the right time to shift to basically a more realistic process that you guys would use. 0.18 micron is what we would say is a very mature process. It's a mature, widely available, reasonably priced process that you would use for analog circuit design. Now, of course, if you go out and work, you can also use 0.13. You can also use 90, and if you're really lucky, you can also use 65 in today's technology. So why is it that we're going to focus on 0.18? Well, for one thing, one of the big reasons this class has used 0.35 in the past is that we want to focus. This is a teaching model. We want to teach you how to design circuits without worrying about all the details that you would have to worry about in real life. You'll get paid good money to do that once you graduate. For now, we want to stress the fundamentals, and if we go to finer line technologies, especially voltage headroom becomes a big issue. Okay, so using something mature like 0.18 will let us get around those issues. We're not going to use other technologies, including bipolar, silicon germanium, HBTs. We'll talk about them once in a while and compare and contrast them, but the focus will be CMOS technology. The model that we have available to us in this class is somewhat experimental. Unfortunately, device models are very proprietary, and I can't just give you a real transistor model that I have, let's say, from ST Microelectronics or TSMC, because that's proprietary. Have to have all you guys sign NDAs, and basically who knows what's really inside those NDAs. You're basically selling your soul when you sign those NDAs. But so what I did is I did a little search on the internet, and I found that Peter Kingett, Professor Kingett at Columbia, has put together a 0.18 model based partly on reality, but it's an instructional model. He pretty much put it together. And the way he did that was on the Moses website, they have postings for basically process variations of threshold voltage and mobility and other key parameters in a transistor, and by using that variation, he's put together a model that has corners, basically. And by corners, I mean you can actually talk about this a little more next lecture, but you can simulate your devices at different process corners. A slow corner, a fast corner, a typical corner. You can change the temperature, and hopefully everything works out well. So I've modified that model slightly. I noticed that the output impedance of that model was a little bit too nice. I wanted to make it more realistic, so I've made the output impedance basically have breakdown effects. We'll talk about that next lecture, or the lecture after that. But other than that, it's the model that comes from him, and there's a big header in the file that explains how he put this model together. If you're interested, have a look at it. It's the first time we're using this model, so there may be a few bugs. We'll have to uncover those together in homework 1 and 2, hopefully way before we get to the project. But I encourage you guys, especially the ones of you who are more experienced, perhaps the ones who took 142 and did the project. You've gone through this process already of working with an advanced model, and you have some more insight. So help me out. Let's make sure this model is good for this course. Okay.